Hello and welcome to Los Alamos National Laboratory's Math and Science Academy. This video is one of several in which we will explore the Common Core standards for mathematics as they relate to teaching about rational numbers. We will be looking at rational numbers through two lenses. First, the sequential trajectory of how we bring in the simple concepts early in the students' learning in third grade and move through fourth, fifth, sixth, seventh, and ultimately eighth grade to expand into irrational numbers. The other lens that we'll look at is through the Common Core's standards for mathematical practice, which are listed here. In each video, we'll be focusing on one or more of these mathematical practices. Finally, in each video, we will be looking at the ideas presented through the lens of something we call IC Flip. IC Flip is an acronym for the way that students begin to see and understand ideas, first starting with the concrete and moving up to the very abstract and procedural. We'll start out with images, which give the student an opportunity to see something in real life that they can connect to. Use that to illustrate a concept. As we get a little bit more abstract, we will bring in some facts and language that will help the students talk about the problem or the idea at hand. And finally, towards the end of the progression, we will look at procedures which are strictly abstract using symbols and are, generally speaking, the most efficient ways, but the most abstract and difficult to understand. In this particular video, we'll be looking at 3.NFA.3a and b, which are about fraction equivalence. There are two other standards, C and D, which are also fraction equivalence, which we'll do in the next video. The two mathematical practices that we'll look at in this video are reasoning abstractly and identifying and making use of structure in solving problems. The specific standard that we'll address in this video comes from the 3NF section, where we're developing an understanding of fractions as numbers. We're going to be looking at 3NFA 3.a, which is where students will understand two fractions to be equivalent if they're the same size, or they end up at the same point on a number line. We'll also be looking at 3NFA.3b, which is to recognize and generate simple equivalent fractions, such as a half equals 2/4 and so on, and really trying to understand why these fractions are equivalent using visual fraction models and also number lines. The two standards for mathematical practice that we'll focus on are, again, SMP2, reasoning abstractly and quantitatively, and SMP7, looking for and making use of structure. The learning goals for the students for this video are, first, to understand that equivalent fractions of the same whole are the same size. It's important to understand about the same whole and this idea of size, which can have different meanings and can get confusing. The other goal is to recognize and find equivalent fractions and then explain why they are equivalent. We'll start with this problem. Use a visual fraction model to demonstrate that 1/2 equals 2/4 and 4/6 equals 2/3. So in this example, we're going to use hexagon tiles. Later we'll look at fraction strips and number lines, which are more linear and lead more towards the abstract version of things. But a lot of folks use hexagon tiles, and they're nice as a more concrete image as we're just starting to introduce this concept of an equivalence of fractions. So we'll start with a whole. This hexagon represents one whole. And in our first example, we're going to try to compare 1/2 and 2/4. So we'll take this whole and divide it into two to be able to create 1/2, which is one part out of two. So there's our half, is the shaded region. And then we're going to do it again. Here's a second whole. And this time, since our parts, our units are going to be fourths, unit fractions are fourths. So we'll break it into 4 pieces. And we're interested in 2 of them. Here's 2/4, and you can see that those 2 areas are the same. And so we see that 1/2 and 2/4 are the same. And of course, it's helpful to add the symbols here to show that 1/4 plus 1/4 is 2/4, That's 2 of these units of a fourth. And so we get that 1/2 equals 2/4. In our second example, we're going to be working with sixths and thirds. So let's do the sixths first. We'll break this whole into 6 parts. And if we're interested in 4 of them, we'll shade 4 of them. And again, it's helpful to use the symbols to show that 1/6 plus 1/6 plus 1/6 plus 1/6 is 4/6. This is helping students start to see abstract notation of what 4 pieces, each of which is a sixth, is, which is 4 of those sixths. We'll take our second one now and split it into 3 parts because we're going to compare against 2/3 and shade 2 of those parts, each of which is a third. And again, 1/3 plus 1/3 is going to be 2/3. So we have 2/3 shaded on this side and 4/6 shaded on this side. And of course, they are the same. So our takeaways here are first that we can write the same fraction, the same piece of a whole in different ways that are equivalent. They represent the same amount of the whole. 4 parts when you break the whole into 6 is the same as 2 parts when you break the whole into 3. And by the same, what I mean is these are the same size, the same amount of the whole. Now it's important to keep in mind that this only works when the wholes are equivalent. And you notice I started with the same size whole over here as I did over here. And that's a crucial feature of this idea of equivalent fractions. I want to point out how this particular process makes use of the practice of looking at and using structure. There's both physical structure here, as in the shape and pieces of the hexagon that we break up, and noticing that when we have 4 of these pieces and each is a sixth, we have 4/6. Or in the case of the thirds, when we have 2 of them, those 2 physical pieces create 2/3. But also their equivalence, the fact that you can physically see and recognize that those parts, those amounts are the same. There's this structure of the actual physical hexagon that helps the student understand this idea. Also in the symbolism, we've got this structure. You'll notice when we add these together, we're setting the stage for adding the numerators, which are the number of, and you'll see 1 plus 1 plus 1 plus 1 is 4. So in the numerator, we're adding them, and the 6 in the bottom represents the unit, the sixths. So that doesn't change. So adding fractions, which we'll get to when we get more abstract in the procedure, we always have to have a common denominator, a common unit, so that we can then add the number of those, which show up in the numerator. So these 2 kind of symbolic representations help us to see structurally what we're going to end up doing later, which is finding a common denominator and then adding numerators when we get to that point. In our next slide, we're going to use the same problem using a visual fraction model to demonstrate the equivalence between 1/2 and 2/4, and also 4/6 and 2/3. But this time we will use a fraction strip and a number line. This will perhaps be a little bit more straightforward to students since we've used this quite a lot. We begin with a whole, and to work with halves and fourths, we'll first split the whole into a half and represent 1/2 here. And then give ourselves another whole, and let's break it into fourths. So this one will be our fourths strip. Now let's shade 2 of those, and we'll get 2/4, also known as 1/4 plus 1/4. And students hopefully can just see the equivalence here, that the same amount of the whole in each case is shaded. This 1/4 plus 1/4 is the same as a half. We can do the same on the number line. Starting from 0 to 1, we'll break the number line first into 2 pieces to give us the half, and now we're going to locate 1/2 as a number on the number line. Instead of labeling this distance, this increment here, we're going to label this point, this position here, which is that subtle difference between 1/2 as a part of a whole and 1/2 as a number. And then we'll do the same with the fourth, but for that we need to split the number line into quarters, fourths, and label 1/4 and 2/4, and we get the same position and see that they're equivalent. This is a very simple and straightforward way to show the equivalence or non-equivalence of two fractions. However, it's based on being able to draw very accurately these breakdowns of the number line. Next, we'll look at 4/6 versus 2/3. You'll notice that we didn't do that with the fraction strip, primarily because we're trying to move students closer to procedure and the abstraction of the numbers here. So I just didn't illustrate the 4/6 and 2/3 as a fraction strip, which you could do, of course, if you need to. But to do this one on a number line, we'll break first into sixths. So here's our sixth, and count out to 4. Here's 4/6. So that's the position of the first one. And next, we'll break into thirds. And in this case, doing that can be done just by removing the sixths ticks. And now we see that 2 of the ticks that we used for sixths are also relevant for thirds, which kind of indicates that there's some equivalence going on here. And now we'll label 1/3 and 2/3 and see that the 2/3 position is exactly the same as the 4/6 position. So you'll notice that in this one, again, I've made use of abstract reasoning and the structure of the number line. There are two standards for mathematical practice to accelerate the thinking process a little bit and find a fairly quick, almost procedure, not quite, it's kind of a visual procedure to identify whether two fractions are equivalent. So our takeaways here are that equivalent fractions are the same place on the number line and that they are the same number. That's really where we're getting to, although we've also shown that equivalent fractions are the same amount of the whole, which is what we showed in the previous slide as well. We'll finish up with some mathematical writing, looking at a slightly different problem. Are the fractions 3/4 and 5/8 equivalent? Use a visual fraction model to explain why or why not. So here is some mathematical writing that we might get from a student. And really what we're looking for in the mathematical writing is all of these different parts of the IC flip framework. Does the student understand the idea from the point of an image? Can they connect it to concreteness? Do they really write some things that illustrates understanding of the concept? Some facts. Is their language use correct? And ultimately, is it moving toward a procedure? In this particular case, the procedure is not going to be a strictly symbolic, quick and efficient mechanism to find the answer, because we're not quite there yet. But we want to see that the student understands the pieces well enough to be able to do them fairly quickly and in a number of different cases, so they can generalize. So the student starts out with a fraction strip model and shades 3 out of 4 after dividing it into 4 parts, shades 3 of them, and then in the eighths divides it into eighths and shades 5 of those. And you'll notice these little dots that they've put in here, which kind of help to see the equivalence of the different fractions. And then they write 3/4, 3/4 is 3 parts out of 4, so they're looking at part whole concept. And 5/8 is 5 parts out of 8, which is this one here. It takes 2 parts of an eighth to make 1/4, so you would need 6 of them, eighths presumably, to make 3/4. This is the concept. That's the concept right here. Here's an image, here's the concept, and then the conclusion. So 3/4 and 5/8 are not equivalent because you would need 6. You'll see facts in here. 2 parts of 1/8 make a fourth. That's a fact. And the language, they're using the language equivalent and writing out the idea fairly clearly. You'll notice in all of these slides that I've used in this video, I've used fractions where they are multiples of each other. I used thirds and sixths, fourths and eighths, halves and fourths. which means that there is some exact equivalence. We will get, of course, to that place where that doesn't happen and where we need to come up with a common denominator and re-break things up in order to have the same parts. But for now, we're just working with this idea of equivalence where we don't have to add that complexity. This video has covered parts A and B of standard 3.nf.a.3, and in the next video, we will look at parts C and D, which are a little bit more complex. Thank you for watching.